Hi guys, welcome back to FEADITH Technologies. In today's video, I'm going to show you how to model a crash tube under impact using axisymmetric approach. So we're going to use axisymmetric elements. So if you want to know about this, stay tuned and don't forget to click like, share, and subscribe. Okay, so let's now jump into Abaqus directly. All right, so this is our Abaqus, and we are going to do the same thing here. Click create part, and we're going to do with 2D planar but it's in 2D shell. Okay, it's deformable and continue and click, because this is the axisymmetric models. Oh, I'm sorry, we need to go back. Make sure you click axisymmetry, not 2D planar. Okay, because we want to simulate a axisymmetric cases right now. So axisymmetric deformable shell, continue. So this is the point of revolution, the way you make it axisymmetric. To draw here, uh, the radius should be 40, I think, and 40,0 to 41.6, how tall is it? 215. Okay, so this is the height of the tube, right? Yeah, the thickness is 1.6. So this point is 40 and this point is 41.6 to include the thickness of the steel. And then click here and click done. As you can see here, now we have only one strip like this. It's a 2D strip, but actually we will use axisymmetry, so it will represent a 3D solid revolving around this axis. All right, so what we need to do now, go to the properties, create materials, the very similar step like in this video above. So if you haven't checked the video, you should check. As I said before, elasticity is 220,000 megapascal, 0.3. Yeah, it's similar to the previous video. You need to check the previous video if you don't understand this. And the data point is the one that we used yesterday or in the previous video, 200 0, 200 MPa 0, and then 255 0.05, and then 350 0.2. Okay, and then for 110 0.4, for 110 0.4, and click OK. Okay, nice. So here we are going to simulate using explicit dynamics. So make sure you also include the density, because in the previous video we also forget, and then we found out that we haven't input it. In that case, 8,000, I think, right? Oh, no, should be 0.08 due to the unit. Check my previous video about this, as I said before, because we explained how to get this data. And then we create section. It's still solid. Okay, remember, it's not a shell like a shell for a 3D. No, that's not it. It's axisymmetric, so you keep using solid, because even though the shape is shell, the shape of the geometry is shell, it's actually represent a solid behavior. So solid homogeneous. Okay, okay, and then you assigned it. You select this, click done, click OK, and since we want to do the very same thing, how to say, uh, let me think a bit. We need to make a partition here, I think. like in the previous video. I don't know how to make partition here. Maybe partition sketch. Yeah, we need to sketch. Yeah, we need to create a line from here to here, straight line, to make partition here. And then we add the dimension, so the distance between this line and this line should be 15 millimeter, right? And we also need to make the second one here. Okay, so make sure when you create this kind of line, there is H symbol, means horizontal, and then I press escape to escape from the, otherwise the line will keep wanting you to click. So you click escape, and if you want to delete this guy, you press Control Z. Yeah, Control Z, you can do it. And then don't forget to make a dimension. It's a 15 millimeter. So now it's all set. You click here, you click done. Now you have a partition here. Why we need this partitions? Because this area will be, how to say, push down into the slit of the fixture, right? So we assume that all this part will be constrained in translation and rotation. Okay, and properties, it's already finished. Assembly, create here, click OK, and step, we click here, static general. Now we're going to use dynamic explicit, right? Continue, nonlinear geometry on, and everything okay. If you want, you can use okay, it's okay. Here we use, I think it was 200, right? Evenly spaced. And also here, the history output, click here, it's also 200, and only include the energy history output, just in case you need it. If you want, even if you don't include that, even if you delete that, the Abaqus can still solve the problem. It's just output request, right? Uh, Interaction, yes, but then we need to make another part for, how you call it, so the impactor. Okay, so let's make the impactor. The impactor, the axisymmetric, but now it's discrete rigid. It's like a wire, right? It's like a wire, I think. Yes. Okay, so it's only like this. I don't know how much should be the length. Maybe 100. No, the radius is 40, the diameter is 80 yesterday, right? If you remember, the size was 80 millimeter, so it should be radius 40, and then we can make it 50, 50,0. Okay, and then press escape and click done. Okay, and this is second part. Then you need to put the, how you call it, reference point, because this is rigid reference point. You click here, you can click here, you can click here anywhere you want. Doesn't really matter because it's rigid. I click here. Okay, and the assembly, I need to create assembly for the impactor, and I click OK. All right, and so, all right, it's like this. If you want, you can impact from above. For example, you can remove this guy and translate it from, what to say, from this to this. Okay, click OK, right? And then you go to step. We make the step, right? Yes, we made the step. And then go interaction. We did the interaction too. Oh no, not yet. So click here. It's a general contact. It's quite straightforward. Abaqus know what to do. and you can create the interaction properties. It's similar to previous videos, nothing fancy here. 0.3, it's a typical friction value. It's always better to have friction other than using frictionless. It's safer. Okay, and then interaction properties. Okay, and that's it. And we go to the load. As in the previous video, we are going to fix all here UI2 state, while this one here, this guy, will be fixed. Click continue first. Click here. This guy can move in the y directions. So, okay, we we constrain the rotation and the displacement in the one directions. Okay, and then the reference point we create for the reference point. So the same thing, x and rotations. And in term now the velocity, we want to put the velocity, but in that case we need to go to interaction again. We want to assign a point mass here, special inertia, create point mass, create. Yeah, you click this reference point, click done. Isotropic, it's 250 kilograms. We are using grams yesterday. I explained in the previous video, right? When I said yesterday, I mean previous video. And then you click OK. And then we go back to the load. And then we create velocity. So they will have kinetic energy because you just assigned the mass. Now you need to assign the velocity. So it will have the kinetic energy, half mv squared, right? That's the kinetic energy. Yeah, it's here. Predefined field. You go to the initial mechanical velocity. The velocity is here. Click done. It's a, how you call it? There's v1, there's v2. Now we are in the z direction, so -6 in the v2. The velocity is 6 meter per second, but in our case we are using millimeter and milliseconds. So 6 meter per second is equals to 6 millimeter per millisecond. So you just need to put -6. That's it. Now it's good. You go to the mesh. I think for the discrete rigid, for the second part, click apply, or you can use, it's in terms of computational time, it should be cheaper because it's just how you call it, a discrete rigid, explicit. Okay, it's just a very limited element. And then here put one, click apply, okay, and then go yes. Here is a meshing part. Okay, it's already mesh. Okay, now it's S4R. It's asymmetric stress, explicit, secondary accuracy, enhance. If you want, you can do it. Done. And note here that you are using axisymmetric element that has a quadrilateral shape. So it has four sides. So it's like it's a quadrilateral elements. So under bending, in order to be able to capture the curvature and the stress variation through the thickness of this wall, this thin wall, you need to use at least 4 elements. Yeah, 4 elements is mandatory to capture correctly. Otherwise, you will never get the same accuracy as using shell element. Because in previous video we're using shell. Shell has rotational degree of freedom. This guy do not have rotational degree of freedom for this kind of elements, right? So you need to use here. You click here, seed edges, and then you click here. Done. And then you tell them to use 4 or maybe 5. 5 is better. Then you click mesh and let's check. Now you have 4. What kind of element this one? They don't usually they have, oh yeah, CAX, axisymmetric, 4 nodes. R means reduce integration. Okay, this is nice. Done. And then you go to the job. I think it's finished, right? It's a very quick tutorial. It's pretty simple and it should be faster. I'm using 2 processor. Then you click here, job manager, and submit. Hopefully there's no error. It should be straightforward. Click monitor here, and it should be really, really fast. With this computer, the previous simulation took me like, oh my god, I have error here. Contact cannot be defined on 2D element facet. With the model content 2D. I don't understand. What the hell is this? Contact cannot be defined on 2D element facets. Okay. So you guys cannot do general contact maybe? You if model contains 2D elements, then contact includes. Okay, maybe you need to really. Yeah, this is something that I just learned. So we learned together here. I thought you can use general contact. Uh, so let's go back. Let's go back to the interaction. Not difficult. It's easy. Instead of using general contact here, we turn off this guy. We create new one. The surface to surface explicit, and then here is a tab. You click continue. Select the first surface. Yeah, the first surface is this surface, the master one. Choose the side we want. The contacting surface will be the yellow, right? And choose the second surface. The second surface is this guy. What to say? Uh, we cannot choose that because so we need to remove this. How you call it? This impactor first. Remove selected. So we remove that. Then we choose this surface. Okay. We're using kinematic contact method. Yeah. Okay. Finite sliding. Interaction properties. We made it before, right? Click OK. And then the other one that we need to, because previously the interaction one is basically general contact. The powerfulness of general contact is that it can detect everything. It can detect self contact between the walls. It can detect the contact between the impactor and the tube. So it's everything is automatic, done by Abaqus. In this case, is that we need to specify one by one. So we need to create a new contact, self contact. Yeah, the contact by itself. By yeah, so the tube wall to its tube wall. Select the surface. Yeah, so you need to select the surface that is contacting to each other, maybe. Okay, done. Oh, must be continuous. Okay, so maybe this guy, put also this guy. So make him happy. Yeah, kinetic contact, blah 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 blah. Yeah, it's basically it's yeah, you need to do it manually. I don't know why. Do you understand why? I don't know why. Why you need to specify manually? Maybe this Abacus guy forgot to implement general contact for the 2D facets or to do the 2D face. So yeah, they will just give you like, if you use 2D, then give this warning error. You need to use, yeah, manually. The error message that we just saw. Yeah, now it works, right? I think. Yeah, you see. So the only problem was that thing, and it's really quick. You see, previous simulation took me like several hours. Now it's like very quick. It's almost done. 200. Now it's done. Not even a minute. Oh, nice. It's a very nice. Oh, but our time is so short. Okay, it shouldn't be one. It should be 25. Yesterday was 25. Now, and 25 was short, right? You haven't fully consumed or absorbed the whole impact energy. Now let's make 50 so we can see the whole process better. Job, submit, and remember this. 25, we click OK. Okay. Okay. So now it start running. Okay, guys. So now it's complete. It's completed, right? It's 12, 200 steps. Frame. I mean, 200 frame. Click results. I already opened it before, so let's close it first. This is how you close. So imagine, no, not imagine. Listen to me. Sometimes during the running, you want to check your results, your intermediate results, right? And usually the frame is not like until 200 frames. It's only 175. It will not update up to the latest frame that has been solved by Abaqus. So how to update it? So what you need to do is to first close the current ODB, close ODB, and here click and okay, it will close and then reopen manually. Open, and this is the ODB. So now if you go here and if you go here, you see that it's already 200 frames. So in previous version or in several computers that I use, sometimes they update automatically, especially if you're using Windows. But in the recent version that I'm using, I don't know. I never find it updated automatically again. So I usually in the last 6 months, I think I need to close down manually the old ODB and then open the final ODB that has been solved by Abaqus. All right. So you see, this is the deformation. It looks good. Ooh. First folding, second folding, and third folding. It's moved up again. I don't know what happened. I don't think it's because elastic energy, because it's just if it's just a release elastic energy, I don't think it will unfold it that much. You see here, it opens like that. I think there's a mistake in the contact. So I believe that this line and this line somehow like has a sticky surface. It's because maybe there is penetration between this line, they are overlapping. So I don't know. Let's check. This is how you check the plastic strain. You will see that there are a lot of plastic strain here. Even with 5 elements, it's already good. But in this case, if you see in this folding, I think it's better to use a smaller elements in the axial directions. In this case, our global axis, no, global sits was 1 millimeter through the whole samples. So we need to make it smaller. I think a 0.5 is good, right? To capture the curvature better. And yeah, that's the only problem. So we can also plot the fill output here. Continue. Now we go to the unique nodal, RF, maybe RF2, right? Reaction force in the second direction from the this, how you call it, this boundary condition. You can highlight, click highlight, and then sometimes they show it, sometimes they don't want to show it. I don't know why. I don't know which one. Let's close and open it again. Continue. Note set. But I think it should be, I don't know which one is this. Tools. Where is it? I Yeah, sometimes they have this problem. They don't want to show which. Okay. Note set, highlight. What the hell? I think it's a set 5, I think. Let's save it. And then you can click here. Oh, there's only one node in the set 4. I don't think that is the one that we want to find. Or maybe it's a set 1. Let's save. Remember, after I save it, I delete it. So, yeah, maybe this one. If you plot, it's like this. I'm not sure if it's the one that we want to find. Okay, let's rerun again. But first, before we rerun again, actually you don't need to rerun. You can just close the Abaqus CAE and open the ODB again, and it will show up. But now, since we also have problems, it's better to recheck again. First, the mesh. Let's make a finer mesh instead of, because our model is pretty light. So instead of using 1, let's using 0.5. So it's better in capturing the curvature, right? So it's the shape of the element is a bit square, right? So it's good. And then you go to the assembly. So usually what happens is that this line is below this line. So what happens is that there is penetration, and then they kind of sticky to each other. So it's better to give a little bit gap. So comma, you enter, and then the second point you move it, I don't know, maybe 1 millimeter or maybe 0.1 millimeter up. So there's a little bit gap. It's okay, just to ensure that, yeah. And then we go to the job, and then you submit again. Okay, and now with the power of editing, here is the result. Yep, here's the result, guys. So it looks good, right? But still there is like a big unloading here. I don't know why, honestly, but maybe because that's the reality. There's a big unloading. There's a big elastic unloads, right? 2, 3 folding, and then it start to push up again because there's like a, the reflection. Yeah. Oh yeah, it's good, right? You see, so it was correct that there's no problem this time, since you can clearly see. Oh, where was it? You can clearly see. You can clearly see. Yeah. So yeah. So from here, yeah. So from here, this is unloading, and then it stops. So the unloading stops here, elastic unloading, and then the impactor bounce back. Okay. So this is good. And the nice thing of axisymmetric, actually, you can, I mean, imagine it's not really good to show this like this in the report. You want to see like a 3D shape. Uh, so you can click here in, I'm not sure which one, this one, I think. Oh, no. I think it should be, where was it? Here. Oh no. Maybe here. I don't know. No, 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 no. Where was it? Or results options. Yeah, result options. Complex form. No, where is it? Here, yeah. It's ODB display option. You click here, and because this is axisymmetric, you want to, how you call it, sweep, not sweep. Uh, yeah, I think sweep, right? Is it sweep? Mirror pattern, yeah, sweep, sweep. Yeah. So this is if you want to see like, uh, yeah, you can go here. So 360, 100. By doing this, you can model this like this, right? It looks good. First folding, second folding, third folding. You can clearly see here. This is the folding, and then there will be a little bit unload. First, second, third, and then there's a big unloading. I didn't expect this much unloading. If you guys know what happened, comment below. But yeah, this is it is what it is, right? Uh-huh. And then you can also remove these free edges, I think, right? So if you show this kind of curve just like this, nobody knows that it is the axisymmetric model. It's just like a 3D model, right? It looks very good. So I hope you understand now how to plot the, oh, now let's plot this guy. Okay. The force time curve, the RF2, edit, not selection. From set, oh, I'm not really sure which one is this. Let's go to here and let's check that which set is the one in the bottom. It's set number one, set one. Okay, so we were right. Job, you go to job, you click result, and then it's this one, set one, save. Okay, make sure we delete it. Oh, now they are double because I forgot to delete the old one. Click delete. Okay, and now you click save. You come back here, save again. Okay, now you have everything, and then you create, you operate on XY data because you want to sum. You type sum, bracket, bracket, close bracket, and then go to the middle, and then click the first one, drag down and press shift and click and add to expression and save as. Okay, so this is the summation, and then you plot. And if you compare the previous video that I have, it goes to 80, around 80, and then go back. So it's around 50 something. So yeah, this is how to plot the force. And if you need the displacement, you can get the displacement of the impactor. For example, you click here, ODB, and U2, unique nodal, and you go for maybe set 4 or maybe a reference point. Yeah, you delete this reaction force, so it's only U2 here. Okay, save. Okay, and now you have the sum of the force and the displacement of the impactor. Now what you want to do is to combine them so you can plot the force and displacement. What you can do actually here, the simplest one is click here and copy this data to Excel, just like this. Right click, copy, and then you click here in the displacement, you take the displacement and copy, and that's how you should do it. If you want to do it in Abaqus, because you want to check first, If the result is correct, you create here, operate on XY data, you click continue, and then you go to combine, okay, combine, and then you click U and X, add to expressions, save as data, click OK. So you have the second data, and then you plot. But now, where is it? The displacement is negative, right? It should be positive. So if you want, you can just simply, before you doing this, you click here, before you combine, you click here, you press negative. So they will put the negative of the displacement. So your displacement will be in positive. So you click save, and then you click here. There's the third data. If you plot, yeah, this is the load displacement curve. So it's very nice right now, right? Uh, I think that's it. What I can tell you for today. We learned a lot. For example, how to make this axisymmetric model and put plasticity in there, and then how to put the contact interaction in axisymmetric case, how to model the impactor using this kind of modeling, axisymmetric modeling. We assign a point mesh with a certain mass, and we create initial velocity, so it will have, the impactor will have kinetic energy, and then they will impact, and there will be a deformation like this, self-folding, and then I'll show you by you clicking here ODB display option. Even though you model it using axisymmetric elements, you can always display this in a 3D form like this. So it's really good for your report or your animation for your slides, right? So thank you very much. Bye. Please don't forget to click like, share, and subscribe.